So in this problem, we need to verify that the relation congruence modulo m on the set of integers z is an equivalence relation. Okay. Before beginning, let's try to understand what is it when we say congruence modulo m. So let's say m is any arbitrary integer. So m belongs to the set of integers. So it could be any arbitrary integer, but it has to be fixed. This m value is going to stay fixed. Then for some integers a and b, let's say for some integers a and b, the congruence modulo m states that if we take the difference of a and b, and this a minus b is going to be divisible by this modulo m. This is the modulo m. So this is when we say that a is congruent to b modulo m. So this is the meaning of congruence modulo m. So to understand this, we'll take the help of an example. So here we will say that 18 is congruent to 3 with modulo 5. That's because if we take 18 and from here subtract 3, what do we get? We get 15, and clearly 15 is divisible by 5. So that means 18 is going to be equivalent to 3, or we can say 18 is congruent to 3 modulo 5. Okay. Now our goal will be to show that the relation congruence modulo m on z is an equivalence relation, which means that first we have to check whether if it is reflexive or not. So to check whether if it is reflexive, so let's say we consider an arbitrary number a. So let a be an arbitrary integer such that if we take a and from it subtract a, then what do we get? We get 0. But what is 0? 0 can be also expressed as 0 multiplied to m. Means exactly the same thing, but the moment we write that a minus a equals to 0 times m, so here what we are saying that a minus a is divisible by m. This is divisible by m, and if it's divisible by m, so we can also say that a is going to be congruent to a modulo m. Fine. So this is what we mean by congruence modulo m. A is congruent to b modulo m, but since we want to show that the relation is reflexive, so we replace this b with a, and we are able to show that a is congruent to a modulo m. So this implies that our relation R is reflexive. Okay, so we have tackled with the first part. Now we'll have to check whether if the congruence modulo m is symmetric or not, if it is symmetric or not. Okay, then what we'll do, we're going to consider two numbers. So let's say let a comma b belong to, so these are two arbitrary integers, so they are going to belong to the set of integers such that, so if we take a congruent to b modulo m, so what does it mean? This simply means that a minus b divides a minus b is divisible by, this is going to be divisible by m. Fine. However, we can also rewrite a minus b as if a minus b is divisible by a, so that means that a minus b is going to be a multiple of m. So here let's say a minus b equals to lambda times m, where lambda is nothing but a integer, some integer. We don't have to worry about this value. We're just representing a minus b as a multiple of m. Now what we can do here is we can multiply both sides with -1 to get b minus a. So b minus a is equals to negative lambda times m, and then we can rewrite it as b minus a equals to beta times m. Now what is beta here? So here what we have done, we have considered negative lambda to be equals to beta, which is also an integer. Now what we have shown here that b minus a is a multiple of m. That means we can say that b minus a is divisible by m as well. So it's going to be divisible by m. If it is divisible by m, then from the definition we have b congruent to a modulo m. Fine. So what we have shown here. So we started out by considering that a is congruent to b modulo m, and we were able to show that b is also congruent to a modulo M. So this simply means that we can say that our relation R is symmetric as well. So this is symmetric under congruence modulo M. Fine. And then finally we're going to check for transitivity. So let's check for transitivity. So transitivity, that means here we have to show that if A is congruent to B modulo M, and so we have B, let's take B, congruent to C modulo M, then it must be true that A is congruent to C modulo M. So this is going to be, if we can show that this is the case, then our relation R is going to be transitive as well. Okay, so let's begin. So here what we'll do, we're going to consider three numbers, so A, B and C. Let these three numbers belong to the set of integers such that we have A congruent to B modulo M. So this is true, and we have B congruent to C modulo M. So this is also true. Now A congruent to B modulo M, what does it mean? This simply means that A minus B is divisible by M, or we can say A minus B. We can say A minus B is divisible. Let's write it down. This is divisible by M. And B congruent to C modulo M, that means that B minus C, this is divisible by M as well. Now if A minus B is divisible by M, then what we can say, that this implies that there exists some unique lambda belonging to the set of integers such that A minus B equals to lambda times M. Similarly, since B minus C is divisible by M, we can say that there exists a unique beta belonging to the set of integers such that B minus C can be also expressed as a multiple of M. So here we can say B minus C equals to beta times M. So let's call this as equation number 1 and the other one as equation number 2. Fine. Now what we'll do, we'll try to isolate B from equation number 1. So from 1, what we have is B will be equals to A minus lambda times M. Okay, so what we'll do, we're going to replace this V back in 2. So number 2, so equation number 2 gives us, so we have B minus E equals to beta times M, but in place of B, what we'll do, we will replace it with A minus lambda times M. Then we have minus C, that's equals to beta times M. So let's rearrange the terms. So we keep A minus E on the left hand side. This is going to be equals to lambda times M added to beta times M. So we have A minus C equals to, so here we can take M as the common factor such that M gets multiplied to lambda plus beta. Okay, so here we have A minus C equals to M times, so let's replace lambda plus beta with alpha, where we have considered lambda plus beta to be equals to alpha belonging to the set of integers, because alpha, we have already considered lambda and beta to be some integers, and their sum is also going to be an integer which we are denoting with alpha. Fine. So A minus C equals to M times alpha. What does it tell us? This is simply telling us that A minus C is divisible by, this is divisible by M. If it is divisible by M, this falls into the definition of the congruence modulo M. That means A is going to be congruent to C modulo M. Then this simply tells us that R is transitive. R is transitive because that's what we needed to show. We needed to show that if A is congruent to B modulo M and B is congruent to C modulo M, then it must be true that A is congruent to C modulo M. So we have been able to successfully show that as well. So since we can say that since our relation R is reflexive, it is reflexive in nature, it is symmetric, and it is also transitive. All three are valid. Hence, we can say that means we can say hence R is an equivalence relation. So a relation R, which is the congruence modulo M, this is an equivalence relation. This is an equivalent relation on the set of integers.